So I learned about Feyman's technique today, in which you try to explain something complicated in a very simple way. And I learned Peterson's algorithm in operating system today, so I'll try to explain it. For that, we'll make our story. So the story goes as there was a mad king. His name was Ares Targaryen. He had two cooks, Walter and White. So he ordered them to make soup as they were very good at cooking now. But he imposed some conditions because he was the Mad King. Well, what can you say? So the condition was the cooks can only put something in the pot. They cannot look what is already inside the pot. They can only put something in it. Second, and if the second condition was they can have only 3 small letters. Yeah, oh, okay. They have a whiteboard in front of the kitchen and they can write only 3 words. That's all. That's all they can write. And most of all, if the broth is spoiled, they will be killed. Now, as they are the royal cooks, they may be asked to come out of the kitchen, leaving the pot behind, to attend to some other tasks. So what happened is, let's say Walter was cooking the soup and then he got called by the queen. Then let's say we don't have the whiteboard. The kitchen is empty. White goes in. He thinks Walter isn't there and has not put any ingredients, and he puts his ingredients in. Let's say he puts in the water and then he goes out. Then Walter comes back, prepares the soup from where he left off. So how do you think the soup will taste? But twice the water that it was supposed to have. It would taste horrible and both Walter and White will die. But now we have 3 words. So what we can do is, on the whiteboard, if Walter or White wants to cook the soup, they will write interested Walter or White. Okay, and they will write also this is interested. Now they'll write time. Time can be 0 or 1. Walter, okay, time can also be Walter or White. Interested Walter, interested White. Turn can be Walter and White. So 3 words: interested Walter, interested White, and turn equal to either Walter or White. So now let's see, how can we use this? How can Walter and White use this to make sure that they do not put anything in the soup if the other is already making it? Let's see. So when I want to let's say make the soup, or okay, say White wants to make the soup, so he writes interested equal to White, interested White, and then he makes White. It's White's turn. And then what happens? He puts the ingredients down. He goes in and He puts the ingredients and he's called for some urgent duty. Now Walter comes in. He sees that White is interested. He writes his turn, and as he is overwriting his turn, there is a chance. There is a chance that White had already put something inside and he was called away. So he'll wait. He'll wait. Now, when White comes back, what he will check is the other guy interested? Is Walter interested? So yeah. And is it his turn? Is it his turn? He'll see no. It's Walter's turn. This means that he can enter. And it's counterintuitive if you think about it that way. So let's try to explain it. Okay. We have two conditions. The other one should be, if the other one is not interested, like if the Walter doesn't even want to cook food, there is no sense of checking anything and White can just go cook soup and everyone is happy. So the first thing we need to check is if the other person is interested, and the second thing that we need to check what it should be. Okay, so we have a turn. Okay, so either it can be Walter's turn or White turn, but how do we use it to ensure that at no moment two cooks are cooking the same broth? So what we do is, if you want to cook, you are interested, and you write your turn. Okay, so if you are interested and if the other is interested and it's your turn, there is a chance that the other one is inside or has left to attend some work. And if you go in, you would spoil the broth. And so what is that we are doing? If we are interested, we'll write interested, and then we make it our turn. If the other one is interested and it's our turn, we don't go in, we wait. We wait. So Walter is waiting right now. White comes in, sees the other guy is interested, but it's not his turn. So he goes in, he cooks the broth, takes the broth out. Since he has made the broth, he's not interested anymore. And so he wipes off the interested White. So Walter can go now and prepare the broth. Everybody is safe, no problem at all. So that's all, and now some formal definitions if you wish. So yeah, I'm gonna try to explain what is what. So Peterson's algorithm is basically using three variables: turn, which can be 0 or 1, and two variables, interested 0, interested 1, which can be either true or false. Before critical section, which is the broth, before critical section, there is an entry section. The gate sort of and the whiteboard. So here is our condition. Whenever you want to enter the critical section, you must first make your interested value equal to true. If you are at the process 0, then you have to make interested 0 equal to true. For process 1, you have to make process 2 equal to process interested 1 equal to true. And then you write turn equal to your turn. So you have executed till here, okay? You have executed till here. And what happens now if the process is preempted? Then if the other process comes in, he'll write his turn and then he'll wait. Now, when the other process comes back, since he has already executed his turn equal to mine, P0 is already executed turn equal to 0, but P1 came and overwrote it. It can enter the loop because he is sure that there is no other process. The P1 isn't in the critical section or he is not making the growth. And the beauty of this algorithm is it has mutual exclusion, it has progress, it has bounded weight, and it is architectural neutral. Mutual exclusion as only one process can enter. Progress as the process which is not interested cannot stop the other process from going in, because we are checking if the other process is interested and it is your time. If the other process is not interested, you can go enter the critical section, no issue at all. And the third is bounded weight. Now, why is it has bounded weight, and whichever process has turn sets the turn variable first will get the critical section first. So it has bounded weight too, and it's architectural neutral because we haven't used anything that needs specific OS commands like test set load. So yeah, I know nobody is gonna watch, but still, thank you for your time. I could do it better though.